The 7 bridges of Konigsberg problem is a famous thing in math, Knigsberg, and I'll show you how we'll solve that. You have probably seen riddles where you have to try to draw something like this, and the rules are that you're not allowed to, once you start drawing, you're not allowed to lift up your pencil. And if you try doing it, maybe you say, okay, I'll try to do this, and you kind of get stuck. Or maybe you start from the top, you're stuck already. Maybe you start from this corner, you try to somehow do it, you keep getting stuck. It turns out it is possible, but you have to start from the bottom left-hand corner or the bottom right-hand corner, and it's able to be done. Those are called Unicursal Tracings, and sometimes they're not possible, sometimes they are, and when they are possible we want to know how to do them, and it relates to this famous Bridges of Konigsberg problem from Euler. The idea of Bridges of Konigsberg is, here is a top view of a city, and this here is water. That's like a river that goes around sort of an island that is in the city. So the city's got this sort of river and an island in the middle, and it's got these 4 what Euler called land masses. The land masses here, A, B, C, and D. And there are these 7 bridges, which are here, 1, 2, 3, 4, 5, 6, 7. And the question was, is it possible to make a tour where I go through each bridge exactly once and visit all 4 land masses? Sorry, you have to go through the bridges exactly once and visit the land masses at least once. So maybe I start from here and I go into A and come back out to C. And as you can see, it seems like I'm making good progress, but now I'm in trouble because if I go down here, I'm stuck on D, I can't get to the last bridge, whereas if I go through here, I'm stuck in A and I can't get to that bridge. So it turns out that it's actually not possible to do the bridges of Konigsberg, and Euler studies this, and I'm going to show you what the issue is. If you count how many bridges each landmass has leading into it or out of it, D has 3, 1, 2, 3. A has 5 bridges, 1, 2, 3, 4, 5. B has 3, and C has 3. And we have an issue here because when something has an odd number of bridges, like the 5, if I start in A, 1, 2, 3, 4, 5, I must end somewhere else, not in A. On the other hand, if I start outside of A, and I actually do go through all the bridges, I have to end inside of A. So if you have an odd number of bridges, and you start outside of a place that has an odd number of bridges, you must end inside that place. So the issue here is if I start outside of B, I also have to end in B. If I start outside of B anywhere, 1, 2, 3, I have to end inside of B. So if I start outside of A, I have to end inside of A. If I start outside of B, I have to end inside of B. So if I start out here in D, I'm in trouble because that's outside of A and B, and I can't end inside of both of them. The rule is, if there are more than 2, if there's exactly 2 odd numbers, you're able to do the path. But if there's more than 2, you will not be able to. So this one ends up being impossible. Here's a more complicated situation, but this one actually ends up being possible because landmass B has 4 bridges, that's even. Landmass F has 1, 2, 3, 4. Hold on a second. I think there's a bridge out there. That's better. So landmass B has 4 bridges. Landmass F has 1, 2, 3, 4, 5, 6 bridges, that's even. Landmass C has 1, 2, 3, 4, that's even. D has 3, that's odd. E has 1, 2, 3, 4, 5, that's odd. Now we look at A, it has 1, 2, 3, 4, 5, 6, 7, 8. So as you can see, there are only 2 with odd numbers. So as long as if we start in D, if we start outside of E, we have to end in E. So if I start outside D, I have to end in D. So the trick is to start inside D and plan to end inside E. And as you can see, I've accomplished it. So that's the trick. Start from an odd, end in the other odd. If there's more than two odds, it won't be possible. Nowadays, we sometimes take the bridges of Konigsberg problem and shrink the landmasses into points, and then draw the bridges become these sort of, they call them, the points are called nodes in this type of math, and the lines, the curves connecting them are called edges. And I could do the 7 bridges of Konigsberg. I could draw the picture this way. This picture corresponds to the same situation. There are 4 landmasses, and there are 2 bridges from B to D and a bridge from D to A, that sort of thing. So this is called a graph, and it has the same rule as before. We can count what's called the degree of each node. This one's 3. This one's 3. This one's 3. This one's 5. And because there's more than 2 odds, this one's not possible to go through. If you tried to, you would get stuck you'd miss an edge. Now this relates to this relates to this problem. So to do this problem, we can count the degree of each node. That's 2. This has 1, 2, 3, 4 coming from it. This has 1, 2, 3. This also has 3. This has 4, and this has 4. So as you can see, there are exactly 2 that have odd degrees. So you start at any one of them. And one way of doing it, as long as I know that I'm trying to reach that node number 3 there, that's one way of getting there. So there's something called Flurries Algorithm, F-L-E-U-R-Y algorithm. And it helps you find the path when there is one. And a good thing to do is to draw a second copy of this. And the way it works, well, first of all, we can check our degrees. So make sure that there aren't more than 2 odds. 1, 2, 3, 4, 2, 1, 2 there, 1, 2, 3, 4 there, 1, 2, 3, 4 there. So they're all even. So when they're all even, you could just pick any starting one that you want. So I'm just going to start at node F. So the rule is you can go any direction you want as long as you don't cut off what's called a bridge. A bridge is, well, this will become more clear when it happens. So I'm just going to go from F to C, and on this other picture I'm going to erase the edge from F to C. So here I am now. Now I have a choice, and it doesn't matter where I go now. I'll show you what's meant by a bad option. But if I go from C to D, that's allowed, because if I erase that bridge, that edge, I'm not stuck. But here's the first time where I have a choice to make. I can either go down to F, or to A, or to B. And the only bad one is don't go to F, because if I go to F, I'll be stuck there. It's easy to see that I'm going to number these. So first I went here, then I went here. Let me erase these degrees that we don't need anymore. That was my first, that was my second. So just don't go down to F from here, because then I'll be stuck at F. So I'll just go from D to A. That's my third. And I'll erase this edge here. Now I'm here at A. And I have a choice. I could either go to B, I can go to B, I can go to C, or I can go around to E. And for this one, we definitely don't want to go to B. Look at what happened if I went to B. I would be stuck. So that line segment is sometimes thought of as a bridge. So don't go over a bridge if you have a choice. So instead, I'm going to go down to C. I'll mark that up as my fourth, and I'll erase this. And at this point, I'm safe because from then on, I'm just going to go down here as my fifth one, and I have no choices here. I have to go here next, and here next, and here next, and here next. 6, 7, 8, 9. As I'm doing that, I'm erasing 6, 7, 8. So the big moment that we had to watch out for was not to cross over a place that bridges two sort of sections. And that's much easier to tell if you have this other graph. That other graph is called the reduced graph. And when you erase edges, it makes it a lot easier to see when you're getting stuck than if you see edges there that have already been used.